Welcome to the first presentation in Unit 5 entitled Isn't It Electrifying? It says, what is a soul? It's like electricity. We don't know really what it is, but it's a force that can light a room. Well, hopefully by the end of this you'll know what electricity is and it won't be a mysterious sort of thing. So, the learning goals for this presentation are that students will be able to conceptually describe the origin of electricity, describe the historical development of electricity in the United States, and describe the factors necessary to produce a functioning circuit. So, number one, here's what we already know. We know that electricity provides the energy to power our devices. Our cell phones, our televisions, our cars all require some sort of electricity in order to start. Electricity can be generated a number of different ways. A lot of times you plug something into an outlet. Sometimes you have something that runs off of batteries, but electricity can be generated in numerous different ways. Also, we know that there are batteries and electrical outlets. Okay, so here's what we learned in the lab. We learned, first of all, that there are three methods of charge transfer. Okay, and we talked about them in terms of conduction, induction, and friction. And additionally, we learned what these particular symbols mean. These are the different circuit schematic symbols that are used to make drawings of circuits. Now, Thales was a Greek philosopher and mathematician. He was one of the very first philosopher mathematicians. He was very famous for being one of the first people to actually measure the height of the pyramids without directly measuring them. He was actually able to use shadows and those sorts of things to do so. And he was actually the first one to record static electricity on amber. So if you have these little amber stones, if you rub them together, it actually generates and stores a static charge. And he was the first person to actually report this phenomena. Now, charges, there are only two types of charges. The first type of charge is a positive charge, and that's where the number of protons exceeds the number of electrons. And the reason why that generates a positive charge is protons are positive, electrons are negative. Okay, if you have 10 protons, which are positive, and you subtract 8 electrons, which are negative, you result with a plus 2 positive charge. If you have a negative charge, that's a situation in which the electrons exceed the number of protons. Something like you have 10 protons and you subtract 12 electrons. When you do that, you have a charge of minus 2. Neutral is not considered to be a charge, it's considered to be the absence of charge. So, when you have a charged object, it's based on protons and electrons. Now, from earlier this year, you should know that whenever you have a charge being generated, it's only because electrons move. Protons and neutrons only move in what's called a nuclear reaction. Now, hopefully, whenever you're generating charge, there's no sort of nuclear reaction. You wouldn't want to drag your feet across the carpet, touch a doorknob, and have a nuclear bomb go off whenever you touched it. So that's the sort of thing that we're trying to avoid here. So instead what we say is we say that electrons are the things that are transferred. Whenever we generate charge, charge can be generated using friction, conduction, and induction. Now what friction is rubbing two objects together to transfer electrons. A lot of times this is done with a cloth and a rod or something like that, but what you're doing is you're using friction to physically remove electrons from one object and put them on the other object. So when you do this, both objects start out as neutral or charged at zero. But when you remove electrons from one object, let's say I remove the electrons from the rod and that goes to the rag, whenever you do that, now the rod becomes positively charged and the rag becomes negatively charged. When you add these things together, they still add up to zero, but individually they are charged. The object with more electrons is negative, the objects with more protons is positive. Okay, induction is where you bring a charged object close to one, but you don't actually touch it. So for example, this negative charge object comes close to the sphere. Whenever it comes close to the sphere, what happens is it actually causes all the positive charges to move to this side of the sphere, because this is where the negative rod is. And that's because opposites attract. Then what I can do is I can touch the other side of the sphere and make all the negative charges move away. The resulting sphere will be positive. One of the things that you can really look at with induction is induction will make if you use a negatively charged object to do induction, it will create a positively charged object. So there's a reversal in terms of generating a positive or negative sphere. Conduction is where you touch a charged object directly. So, for example, I have a charged object that's negatively charged. I come and I make contact with a sphere that is neutral. Some of that charge will be transferred to the sphere, and now I have two negatively charged objects. So, the thing that makes something conduction is that it's transferred by direct contact with something that is already charged. Okay, the fundamental question says match the term below with the contact of the charged object, based on the contact of the charged object. So we have conduction. Conduction requires direct contact with a charged object. So that's right there. Friction requires direct contact but with no charged object. So you can rub two neutral things together. And induction requires no charge whatsoever, or excuse me, no contact whatsoever with a charged object. How is charge transferred via lightning? So here you have a charge differential right here. You have positive charge and negative charge, but there's no direct contact between them. So induction occurs whenever we're dealing with lightning. Now, if you look right here, it says coming into direct contact with a doorknob will cause you to be shocked. How do you become charged to begin with? Okay, so direct contact that you have between you and the doorknob is conduction, and that is true. But what this thing says is how did you become charged, or how did you become charged to begin with? Now, the most likely reason why people become charged is during the winter months they tend to drag their feet. When you drag your feet, you're creating friction between the soles of your shoes and the carpet. You're transferring electrons either from you to the carpet or the carpet to you. The resulting factor is you become positively or negatively charged. Whatever charge you have then is transferred to the doorknob whenever you come into direct contact with it. Finally, it says give an example of each method of charge transfer using the Van de Graaff generator. So that's what we did in the first part of the presentation. If you put your hand directly on the Van de Graaff generator and then you turn it on, you are being charged by conduction because there is a direct contact. The belt that rotates, causing the charge to be generated in the Van de Graaff generator, removes electrons by friction. So friction is how the Van de Graaff generator actually becomes charged to begin with. Conduction is where you put your hand directly on the sphere. If you take a discharge wand, some sort of metal wand, and you bring it close to the sphere, what it'll actually do is it'll actually discharge without direct contact, and that's generally because of induction. Now that we know a little bit about charge, we need to talk about the transfer of charge through a circuit. Now, one of the key things that all circuits need is some sort of battery or some sort of voltage source. Okay, a voltage source is what provides the energy to a circuit. Now, generally when we talk about batteries, we talk about something that has a positive terminal and a negative terminal. In other words, you have two charged sides of a battery. Now, what can happen is charge can move from one side to another. Now, we know that positive charge generally doesn't move. It's the negative charge that can move from one side to the other. It's that attraction between the positive and the negative side that actually causes electrical current. In reality, the electrons don't move. It's energy that does, and that actually is what makes it much faster. Electrons don't move very fast along a wire, but you can still think of it as charge because the objects become charged as the energy flows through them. Now, a circuit requires a voltage source. Now, that's what we talked about with a battery. The battery is the voltage source, or you can plug it into a wall, or there's something called a variable voltage supply, but it needs something to provide the energy to the circuit. Now, it also needs a charge to be able to move from the negative terminal to the positive terminal. In other words, there needs to be no breaks in the circuit. When there are no breaks in the circuit is considered to be closed. Okay, a closed circuit is one that works because there are no breaks in the circuit. An open circuit is one that does not work. Now, voltage sources, we've already talked about our batteries, but can also be electrical outlets or variable voltage supplies. So for the purposes of this class, we're going to refer to all voltage supplies with this symbol. That is the circuit schematic symbol for a battery, and what it does is it provides the push that moves charge through the circuit. Now, a lot of times we'll use a variable voltage supply, like you see here, because it allows us to vary the voltage provided to the circuit depending on what we want to look at. This particular model allows you to go from 1.5 all the way to 15 volts, and you can increase it step by step. You can get the um, same basic idea by adding batteries. Each one of these batteries is 1.5 volts. So if I wanted to get 3 volts, I would just add two batteries together. When I have two batteries together, I would get 3 volts. The voltage of a standard American outlet is 120 volts. You generally only get about 110 out of it, but what it is it's rated for 120. Now you have a connection or a wire, which is represented by a straight line. Straight lines are the way that you connect the different devices of a circuit. So you can connect things that are like resistors or something along those lines. But what it does is it's the path that allows the charge to move to the other end of the battery. Now, it allows the charge to move through it. Now, wires are generally made out of conductors. Conductors actually make the best wires because they easily allow charge to move through them. Now, if you think about an electric circuit like a system of pipes, what this is the water is flows through the pipe. So it's like a pipe that connects the various things together. Next, you have the devices. Devices, or generally what we do is we call them resistors, are signified by this symbol right here. A resistor is something that actually uses the electrical current. In this case, it could be something like a light bulb, or it could be something like one of these. These are what we think of when we think of standard resistor values. Now, generally speaking, the way a resistor works is it slows down the charge as it moves through the circuit. When it does that, it actually heats up, and it uses that heat either to illuminate something like a light bulb or to just create heat like you have with these resistors. Now, if you think about our water analogy where the battery is pumping the water through the pipes and the wire is the pipe, this is something that actually uses the energy of the water. So it's like something that turns a turbine. Like if you've ever seen they put windmills, or excuse me, mills right next to the river, because what happens is the water can actually push this thing and make it turn. The devices are the things that actually use the fact that this is going on. So everything that uses electricity you would think of as a resistor. Next, you're going to have a switch, and the switch can be in an on or an off position. Now, we've already talked about that whenever you have an open circuit, the open circuit means that it's off or it's not functioning. Whenever it is closed, the switch is acting as a conductor, so it is on. So on means closed and off means open. And a lot of times people have a hard time distinguishing between that. If we look at our water analogy, this is like a faucet that can turn the water on or off depending on the way that it's turned. This is the circuit schematic symbol for a switch. And in fact, here, this is representing a closed switch. This right here is representing an open switch. So here the circuit would not work because there's a break in the circuit and there's no way for the charge to go from here to here because there's a break in the circuit. Here there is no break in the circuit. These things are connected. Because they're connected, charge can flow. Now another device that you often see in circuits looks like this. It kind of looks like a resistor at first glance, but you notice there's only two of them and these things are rounded, so you have two little bumps right here. What that represents is it represents a fuse or a circuit breaker. And a fuse or a circuit breaker is something that allows, that will melt, and it will actually stop current from flowing through a circuit. It'll stop charge from moving through a circuit. It only does that if the current gets above a certain value. So for example, if you have a 10 amp current, or excuse me, a 10 amp fuse, and this 10 amp fuse all of a sudden has 12 amps of current in it, it will stop functioning. What happens is this thing melts, it breaks the circuit, and when it breaks the circuit, there's no charge at that point. If it is not exceeding this current, there's a resistance of 0, and we'll talk more about resistance later. Now, whenever you draw circuits, we always draw starting at the positive terminal. And the positive terminal is the long end that's there. Now, what this is a relic of the day that they thought positive charge moved through the batteries. So we consider this to be the beginning or the start. Okay? Once we've established what the start value is, you need to realize that you need to draw all the different circuit schematic symbols that we've talked about. The different circuit schematic symbols we've talked about, such as resistors. Okay, you'll see things like fuses. You may even see things like ammeters or voltmeters whenever you look at these things. So you need to be prepared to look at the different symbols. But one of the things that you have to have in order to have a functioning circuit is there must be a complete closed path to go from one end of the battery to the other end of the battery. Now, match the symbol with the names below. So based on what we know that the battery has a positive side and it's what moves the charge through the circuit. We know that we have a switch right here that can turn it on or off, and specifically we would want to name this an open switch. We know that we have resistors that actually function to do whatever we're talking about, and we have a fuse. You should be able to recognize what these pictures are and name them. In addition to that, not only do you have to know what they are, you need to be able to say what the function of each device is. So if you look, it says a safety device preventing current. So that would be a fuse. Now a switch can also stop current, but it's not considered to be a safety device. It's something that actually allows, it can stop or allow the current. So we call that the switch. Now something that actually uses the electrical energy, we would say would be the resistor, and then provides the energy to the circuit is the battery. Oops. Now it says draw a circuit with a battery, fuse, and resistor and a closed switch. So the first thing we do is we start with a battery. Now whenever we start with the battery, we always start with the positive end, which is the longer one. So if I go from battery, I can come down and I can draw the symbol for a fuse. Now if you wanted to go straight here and draw the symbol for the fuse right here, that's fine as well. It doesn't matter whenever you have a turn right here to go from, sideways to up and down. Now at this point I have a fuse, and the next thing I need to do is I need to draw a resistor. So I draw my resistor. And we try and make these more sharp points to differentiate them between a fuse and a resistor. And then next, we actually draw our closed switch, and how we do that is we kind of draw this symbol right here, and that symbol right there lets us know that we had something that was, I can open if I want to, and then finally you go to the negative terminal of the battery. Finally, it says mastery B4, it says bulb A goes out, so bulb A breaks. It says what happens to bulb B, C, and D. Now remember, bulbs B, C, and D will work if they have a way to get from one end of the battery, the positive terminal, to the negative terminal. So if I were to look, charge that goes through D can go through B and to the other end of the battery. Because of that, I know D and B will function. But also, instead of going this way, if I went through C, C will also work, because if I go through C, I can still get to the other end of the battery. Now the reason why it won't work with A is because when the charge goes this way, it stops and it can't make it to the other end of the battery. So bulb A will not work.